Thanks for the introduction. Hello, everyone. My name is Tianyi Liu, and I'm glad to be here to talk about the HardTaint production run dynamic tint analysis via selective hardware tracing. And all the authors of this work come from Nanjing University. First, let me introduce some basic backgrounds about the tint analysis. There are typically three key concepts. Tint sources are used to mark the origin of the tinted data, and tint sinks are points where the corresponding tint status is checked to determine where a potential risky behavior has occurred based on the specific application. And tint can also propagate according to the semantics of the program instructions. Tint analysis is widely used in various fields such as bug detection, program diagnosis, privacy, and software security. Compared to static tint analysis, dynamic tint analysis offers higher precision. It dynamically maintains tint information within the program during runtime. However, dynamic tint analysis suffers from high runtime overhead, so it only works for debugging and testing environments and cannot be used for production run usages. To reduce the runtime overhead of dynamic tint analysis, existing works can be broadly categorized into three types. The first type utilizes program analysis to reduce unnecessary tint tracking code. However, due to the inherent limitations in the soundness and completeness, the performance improvements are limited. And the second type uses specialized hardware components to collect information and speed up the process of tint propagation. Such approaches, however, struggle to accommodate a wide range of tint analysis requirements. And the third type decouples execution by separating tint propagation from the source program and offloading it to other processes. Unfortunately, these approaches suffer from high online tint information collection overhead and also increased the latency of the analysis. Despite the above approaches, their runtime overhead on the spec benchmark still ranges from 170% to about 300%, which is far from production use. To further accelerate tint analysis, our insights are that modern hardware tracing models offer the capability to capture the execution information, for example, the control flow and the values of registers with very low overhead. And besides, we can follow the decoupling design, leverage hardware-based tracing to collect tint information online, and do tint propagation on the fly. Although the idea is simple at high level, doing this efficiently and precisely is non-trivial. There are mainly three technical challenges. First, even we are using the hardware tracing all the tint information still leads to high runtime overhead. And secondly, naively recording the intensive tint information via hardware results in severe data loss. And this is because the bandwidth of the hardware trace output is limited. And third, performing tint analysis on the massive scale trace data is costly and efficient. For the first two challenges, we need to use static analysis to reduce the amount of data collected from hardware. And for the last challenge, we do the tint analysis in parallel to reduce the latency of tint analysis. To address the above challenges, we have designed and implemented the HardTaint system. Here shows the workflow of HardTaint. We have proposed a static identification analysis that, based on the tint configuration, it analyzes the necessary tint information to be traced in the program. Then we rewrite the binary so that the hardware only traces the data of interest. The rewritten binary will be executed on a CPU that supports Intel PT, generating the corresponding trace data. In the real-time parallel, use high-speed RDMA network to immediately transfer the generated trace data to another host, and for parallel decoding and parallel tint analysis. We consider the time gap between the trace generation ends and the tint propagation completes as the analysis latency. And let's use a toy example to illustrate how HardTaint works. First, figure A is a snippet of the original binary code. To perform tint analysis, we need to trace the path of data transferring. So we need to know the control flow transfer and the memory addresses that have been used in the program execution. If we naively tracing the taint, we would need to consider 7 points in total. That are the branches and the memory addresses used in the binary, and they are marked red in the right figure. However, after our static identification analysis, only 3 points need to be traced. And based on the trace point information, we insert statements at the corresponding locations in the binary to record the values. After that, upon execution and decoding, we obtain the corresponding taint data. As shown in figure F, we could know the value of the EX register at L1 from the trace output, and the program control flow takes the L6 branch. And finally, this information is mapped back to the static taint graph, where taint propagation starts from the taint source, and the taint status is then checked at the taint sync node filled in the orange color. Next, we will elaborate the key technologies in HardTaint. And the first is the static identification analysis. Exact control flow are essential to dynamic taint analysis. One of our insights is that not all memory addresses or instructions involved in taint analysis must be recorded. So we consider filtering out unnecessary information from tracing. The 3 main optimizations are used to reduce redundant information from register values, blocks and functions, and loop iterations. In the first optimization, redundant registers elimination, we built value flow graph for each function, and we will only fetch the root register in each weakly connected component of the graph, and other register values could be inferenced from the fetched register. The second optimization is redundant blocks and functions elimination. Only a few basic blocks and functions are relevant to the taint, so we can get the reduced control flow graph by removing taint unchanged blocks. And on the other hand, if one basic block is recorded, the execution paths of other blocks could also be inferenced if there are dominance relationships between them. So we can also remove the blocks and functions that could be inferenced. And in the third optimization, we also found that a large amount of trace data is generated by just a very simple loop, similar to a memcopy or a string compare function. If the loop is control flow independent, we can trace the control flow just once. And if the loop is data independent, we can also trace the register values just once. The idea is also simple, but is effective in the real-world applications. And after identifying the points that need to be traced, we perform a selective rewriting of the binary. This allows the hardware to selectively trace the taint information we are interested in. Here we use the PT-write instruction provided by the Intel PT to record the required register values. And since the trace data of Intel PT is highly compressed and cannot be directly used for analysis, a decoder is required to recover the taint information. However, the current decoders only support sequential decoding, take acceptable time for processing the huge trace data. We observed that there are many synchronization point packets, that is called PSPs, in the trace data, and the data between synchronization points is independent. And therefore, we partition the trace data as these PSP packets and assign a decoding thread to each partition. After decoding the trace data, we are going to perform the taint propagation. In the last step, the trace data is split into partitions, so it's straightforward to do taint analysis for each partition in parallel. But since the taint analysis partition may have data dependencies from its preceding partitions, it has to wait the preceding propagation to complete. In HardTaint, we propagate the taint status with best effort. If the dependency of a node could not be satisfied, it will be connected to a dependency graph and wait for the preceding propagation. And finally, about the implementation, we utilize the existing tool to implement static analysis binary rewriting. hardware tracing and parallel decoding, and also the taint analysis. We have also conducted evaluations on a rich set of benchmarks, and we intend to address the following 4 research questions. How well does HardTaint perform? How about the impact of runtime selective tracing and real-time parallel analysis? How does HardTaint perform compared to the state-of-the-art approaches? How effective is HardTaint in detecting taint vulnerabilities? First, let's look at the overall performance of HardTaint. In terms of runtime overhead, HardTaint only introduced 8.6% runtime overhead on average, and it can timely report taint analysis reports with an average absolute latency less than a half second. We also evaluated the impact of varying numbers of threads on the throughput of taint analysis. The average throughput increased gradually with the number of available threads. And at 32 threads, the analysis throughput exceeds or approaches the one of the trace generation, and the high throughput supports to realize the low latency of analysis and timely analysis reports. To understand the impact of runtime selective tracing and real-time parallel analysis, we compare HardTaint with software-based tracing and naive hardware tracing. It shows that hardware tracing significantly reduced the runtime overhead from 500% to 82%, but suffers from severe data loss. Further, utilizing identification analysis and selective tracing leads to a further runtime overhead reduction to only 8% without losing any data. We also conduct the comparisons between HardTaint, StrikeTaint, and taint pipe, the state-of-the-art decoupling approaches. Thanks to the holistic design, HardTaint outperforms StrikeTaint and taint pipe 20 times and 17 times faster, respectively. The relative analysis latency is also significantly smaller. Finally, we also evaluated the effectiveness of HardTaint. We considered 8 real-life CVEs, and HardTaint can successfully detect all of them. And that shows the capability of the precise taint detection. And to sum up, we have developed HardTaint, a system that can realize ultra-low overhead and precise dynamic taint analysis. We adapt a hybrid and a systematic design which combines static analysis, selective hardware tracing, and parallel graph processing techniques to address the challenges. And the evaluations also shows that the low online overhead and the analysis latency of HardTaint, and also its effectiveness. Yeah, and thanks for your attention. I'm ready for any questions. Thank you.
Thank you, Tianyi. We have plenty of time for questions. So maybe I can start. So can you say something about the kind of hardware support that you are taking advantage of here?
Oh, yes. We are using the Intel PT that is, and we are using the PT write instruction that comes from the 12th generation of the Intel CPUs. And it's also possible to use other hardwares like ARM chips. It's also okay, but the current implementation of the ARM CPUs will drop about 90% of its trace data. That's the taint analysis will not be precise enough.
Oh, very nice talk. For the binary rewriting that you do you use an off-the-shelf binary rewriting tool, or do you have like your own specialized tool?
We are using the Divine-Inst tool.
One more time?
That is called the Divine-Inst.
Okay. I don't know that tool. Okay, that's why I'm pausing. All right. But that's clearly not your tool. You're using somebody else's.
Yes,
yeah,
yes.
Okay, very good.
Any other questions? Okay, so I have one more question then. So do you think some of these ideas could be used for also getting efficient taint analysis for more high-level languages? Or is this very much tied to the binary code?
high-level languages. Yes, but the identification analysis needs the whole control flow graph to be static. And if there are too many dynamic features in the language, we must do many special judges on the trace points, and it will significantly increase the overhead. Yes, and I think for currently the HardTaint is able to use with maybe CPP and Golang is also okay. Yes, but I think Java Python is not good.
Thank you. Any further questions? Not, let's thank the speaker again.